Okay, so continuing with the converging nozzle, we are going to discuss choking and the relation with m star and m star with m and other things. So before we start, I will write down the equations for something which we have derived earlier on. Okay, so the continuation of whatever we had discussed in the previous class. So this is something which we have derived few classes earlier. So I will start from this equation today. And a by a star to be 1 by m into 1 plus gamma minus 1 by 2 m square divided by gamma plus 1 by 2 the whole raised to the same exponent. Okay, so we will start from these equations, try to see what we can get in relation to converging nozzle. So if I let us take the first equation. So if I draw my variation m1 and m2, if my a2 by a1 is equal to 1, so if a2 by a1 is 1, my a2 equals a1, which means I am talking about a constant area duct. Remember, this equation is isentropic and quasi 1D. Okay. So with that assumption, if I substitute this, my m1 is always equal to m1 because there is no area change, dA is 0. So whatever m1 I have, it's same as my m2. So I would get a 45 degrees line here where a2 by a1 is 1. If it is less than 1, so this is m1 equals 1 and this is m2 equals 1. So for area ratio a2 by a1 less than 1, I would get a curve something like this for some value of, let us take 0.7. So this would be my 0.8, this would be my 0.6. Okay. So depending on the area ratio, I would have a curve like this. And if my m1 is supersonic, again I would get a curve which would be coming like this, and this equation does not distinguishes between supersonic and subsonic flows. So if I continue this curve, this would be something like this, and this would be something like this. This again for area ratio a2 by a1, say 0.8, 0.7, 0.6. Okay, the shape of the curve would be something like this. Okay, so now let me redraw this just for one case for explanation purpose. I have a2 by a1 1 and this would be my m equals 1. M1, M2, and my A2 by A1 0.7. So, let us take this as 0.7. And this again point 0.7. Okay. For M, M1, for M2 less than 1. So, I am considering only my subsonic exit case. So, what is this figure? This is A2, this is A1, A2 by A1 is fixed. Okay. So, if you look at this, for a given M1, M1 is less than 1 or M1 greater than 1, M1 subsonic or M1 supersonic, I have two solutions here for A2. Okay. For a given A2, I have two solutions, A2 by A1 there are two M2 solutions for a given M1, or no solution for a given M1. Okay. So, if I have either two solutions or no solution. For this M1, I have two solutions, one is supersonic, one is subsonic, or I have for these range of M1s, I have no solutions for this particular case of A2 by A1. Okay. I did not talk anything about P0 or PB or P exit. All I am talking here is in terms of Mach number. If my Mach number, inlet Mach number is between this value for this particular range of A2 by A1, I do not have a solution. Okay. We'll see what exactly that is. Okay. Now, we are trying to understand what this picture is. So, let us do this small exercise. I have a P0, I have a PB. Okay. Let us assume PB by P0, like what we had done in the last class, PB by P0 is somewhere around 0.8, which is greater than your P star value, P star by P0. So, the exit, we know that the exit Mach number is not 1. So, this is somewhere between less than 1, and I have A1 here, A2 here, A2 by A1 is some value, okay, some value where I have a solution. Okay. Now, whatever I do to area or inlet Mach number, my exit Mach number, if it is this value, if you are already reached your critical pressure, the exit Mach number is always going to be 1. But now, this is a case where it is less than 1. So, let us so if my P by P0 is 0.8, the Mach number here is going to be, I look at the tables and what is the Mach number? If PB by P0 is 0.8, .57. 0.57. So, unless I change this pressure ratio, this exit Mach number is not going to change. Okay. So, I have an exit Mach number of 0.57, which depends only on your pressure ratio Pb by P0. Okay. Now, given this situation, now I am going to change my A2. So, I decrease my A2. Okay. So, I am decreasing my A2, which means I am progressively decreasing my this ratio. Okay. So, I should be in this curve where this is A2 by A1 decreasing. Okay. So, I would go from this curve to this curve. Now, my M2 is fixed. Okay. So, my M2 decided by my pressure ratio is fixed. So, whatever I do, it should be on this line. So, I have changed A2 to a lower value, which means that from this point I have a new value that is here. Okay. So, from this value now I have a new value. Okay. So, my A2 by A1 is reduced, my M2 is still the same. So, what has happened here is my M1 has changed. So, if I keep my stagnation pressure same and the back pressure same, my M2 will not change, and in this particular case if I change my A2, I do something so that my M1 is changed. Okay. So, if I change my area, my exit Mach number is not going to change, but my M1 change, which means that I am essentially changing my static quantities at the inlet, and that is what this curve tells you. Whereas, if I keep my M1 constant and I am not worried about how Pb and P0 change, and I keep decreasing my A2, I would reach a value here. Okay. So, I have the flexibility of changing these pressure ratios. So, the next example is P2, Pb, and I am progressively decreasing my A2. Okay. So, I have no control on P0 and Pb. Okay. So, it can change any value, and let us assume it is going to be some condition where Pb by P0 is less than P star by P0, which means that the exit Mach number should always be 1. Okay. Implies your M2 is always 1. So, I have this line. So, my exit Mach number is always 1. Now, I do something, I keep M1 constant, I do something which means I can this can take any value. So, if my M1 is kept, somehow I force M1 to be some constant value and I change my A2, I see that for some value of A2, I have this case in between I have no solution. Okay. I see that there is no solution to this isentropically. So, there is some non-isentropic process that is going to happen which will automatically change my M1. So, this is not a possible way of doing it. So, my M1 will somehow be changed. Okay. There will be pressure waves that is going in this direction, which will change my static quantities and change the pressure values. All right. Now, if you look at this particular case where my A by A star, I will rub this plot. I always have some curve like this, okay, which gives me 1 here. This is when my dA is 0. So, at dA 0 I would have m equals 1 and hence I have a star condition here, which is precisely what is happening here if my pressure ratio is less than the critical pressure ratio. So, if the critical pressure ratio for gamma equals 1.4 is 0.5 to 8, if the pressure ratio is less than that, I am always going to get m2 equals 1 whatever you do, and that means from our previous plot, if Pb is always, or for any condition Pb less than P0, my m2 is always 1, implying my m2 is my m star and my a2 is my a star, because that is the condition in which you are chalking the flow. So, your m dot by a root of T0 by P0 mass flow rate would be maximum at m2 equals 1, which is equal to your m star. Okay. So, this maximum flow rate you are achieving at some conditions where which depends only on your pressure ratio. Okay. So, depends P star by P0, which is a constant. So, if your Pb by P0 is greater than P star by P0, then your mass flow rate depends on Pb by P0. If Pb by P0 is less than P star by P0, then mass flow rate do not depend on Pb by P0. Okay, so, the maximum mass flow rate will depend only on your P star by Pb. So, now we have talked about the chalked condition and the existence of m equals 1 at the exit, which implying that the area at the exit is now the star a star value. We will try to find a relation between m star and m. So, my m star is defined as V by a star, which I would write it as a by a into a by a star. So, I would square this. Should be m square into a by a star square. So, now we will get substitute a by a star from our energy equation, which tells me Cp T1 plus V1 square by 2 equals Cp T2 plus V2 square by T2 for an isentropic flow with no heat and no shaft work, and I replace Cp with any condition T plus, and Cp I would replace it with gamma r by gamma minus 1. So, state 1 is any state. So, I will remove the suffix 1, and 2 is my star condition. So, I would replace 2 with my star values. V star I can replace it as A star by 2. Now I divide the equation with A star. So my A square by A star square plus V square by A square. Okay, so I will divide it with A square, gamma minus 1. Okay. This is 1 by gamma minus 1 plus V square by A square is M square. Okay, so this is 2 gamma minus 1, the 2 plus gamma minus 1 M square. Okay. A star square by A square into 2 gamma minus 1 gamma plus 1. Okay, cancel the denominators. Okay, so this would be 2 plus gamma minus 1 M square by gamma plus 1 equals A star square by A square, which you can substitute here in this equation, and you will end up with a is gamma plus 1 by 2 M square divided by 1 plus gamma minus 1 by 2 M square, or M square equals 2 plus gamma plus 1 M star plus 1 minus gamma minus 1 by gamma plus 1 to M star square. So when M equals 1, your M square is M star is also 1, M is less than 1, M star also less than 1, M greater than 1, M is also greater than 1, but when M tends to infinity, your M star tends to root of gamma plus 1 by gamma minus 1. Okay. That is the advantage of having M star. So, you talk everything in terms of M star. So, associated with any M, you can have an M star. This is again, as we had learned, it is a typical reference quantity. So, what does this mean? If I have a fluid at M equals some value, I do an isentropic process to take it to M equals 1, and the Mach number there is my M star. So, in the TS diagram, I have a state 1 here, I do an isentropic process such that the velocity 0 is my stagnation state. Now, I take it to a value where V equals A, meaning M equals 1, that is my star condition. So, my M star is my V by A star. So, this is my star value. So, the m star associated with this particular m is my m star. Okay. So, m1 if m equals 1, I will have m star equals 1. Okay, so, this is my star condition. Okay, so, this is precisely the process what we are doing in a converging nozzle. So, I have an m here, I have an m here. So, I bring this m to isentropically to this value. So, I get an m here which is equal to 1 if it is less than critical pressure ratio. So, my m star here is also 1, but the m star here is not 1. Okay. Because associated with this m you have a different m star. Okay. So, m star is not constant, only your a star is constant in an isentropic flow, your m star is not a constant. So, I will end with whatever we had done previously. So, we will compile whatever we had done previously by changing your PB. So, I have a typical area ratio. So, P0 is kept constant, this is also kept constant. What we have done is we have decreased our PB. So, when P0 equals PB, there is no flow, otherwise you would get a subsonic flow if PB by P0 is greater than your P star by P0. Your PB will also be equal to your P exit at this condition, and when it reaches the critical value you would get your m equals 1. Any further decrease in your back pressure will not change the flow inside or at the exit, but after the exit there will be some phenomena that is happening which we have not discussed yet, which will be discussed later. So, this is what happens when PB is much less than your critical pressure ratio. Okay. Now, if I change the area ratio, the exit Mach number is not going to change, it depends only on your pressure ratio. We have also seen that from the plot there is a for a given M1 there is a minimum contraction ratio where you have solution, and above which the Mach number does not give you a solution for that particular contraction ratio. Okay. So, to have a steady state flow of your M1, so if this is my this is M1, this is M2, this is for some typical A2 by A1. For a steady flow of your M1, there is a minimum contraction ratio above which you are not going to have a solution. Likewise, if the flow is supersonic, there is a minimum M1 or a maximum contraction ratio with which you are not going to have a solution. So, we will discuss that scenarios in CD nozzles little later on. For the time being, this is more important. We will come back to those curves when we discuss converging diverging nozzles, and it is also important to realize that your M relation between your M and M star. So, associated with any M you will have an M star. So, this you will see also in your isentropic tables. along with your Pb by P0 values. Associated with m, there is an m star, which is a reference quantity again. Okay. Thank you.